Live, hooray. So last time we wrote a parser for let constructs and identifiers in expressions to parse stuff like this. And now obviously we want to interpret these expressions. So we need to extend our interpreter. Felix, have you implemented that?
No, I haven't yet.
Okay. Have you thought about what kind of a data structure you would use for the variable bindings?
You mean for the like for the parser what we used to get the to get the variables?
No, what I mean is for keeping the values of the variables at runtime when you're executing the program.
Oh, okay. I don't know. My guess would be a struct, just for the variable name and the value. If you know what I mean.
Yeah, but then let's say you execute something like this, right? Where you go like, oh, okay, so A has value 10, right?
Oh, right, yeah.
And now you get in here and you say, well, but now A has value 1.
I would have made two separate lists then, because you can't access the A inside. Well, if you're inside the in statement, so inside the let, you can't access the A outside of it, right?
Yes, that is correct. You can only access the most recently defined A. Yes.
Okay, so well, either maybe just scrap the names and maybe just use indexes, or use separate lists with with a variable list outside of the let statement and a separate variable list inside. If that is clear.
Well, there can be any number of nestings, right? So
right,
you would have to have more than two. Like you would have to have potentially an indefinite number of lists.
Right.
Which is fine. Like you can do that.
But not efficient.
With this interpreter, we're not too concerned about efficiency yet. We're doing that later. We're just concerned about making the program run. So yes, both of those are possibilities. So the first one would have essentially been doing something like this transformation, right, where each variable actually gets a unique index, and you don't have to worry anymore. You don't have to worry about the same name overriding anymore because each variable is actually distinct. But that means that before you get to you need to do this transformation, right? So somehow you need to go from this to this, right? So you have to do some program transformation first. But yes, it's certainly a thing you can do. But we're too lazy to do that. I'm too lazy to do that.
Oh.
But certainly our compiler later, both the compiler that compiles to virtual machine as well as to machine code, will have to do some form of this program transformation. So we'll have to learn how to do it anyway. But not right now. But what you said was, if we look at, so let's say, in terms of data structure, so one thing we could do is we could just have one dictionary maps from name to value, let's say. And then if you enter another let that says, for example, let A equals A plus 1 in something something, right? What you could do is you could say, I'm just going to update the A and give it its new value, but I'm going to remember that before A had value 3, right? So you take all the values that you've updated and put them in a separate dictionary, and then once you're done with the let, you make them go back. Right?
Okay. Yeah.
That's another way to do it. Yet another way to do it is actually to have the dictionary map to a list of values, right? And then when you update, what you actually do is you put in the new value first, and you keep the old value, and you remember that we changed A, right? So once you're done, you just pop off the last value and you're back to the old value. Right? Yet another way is to make a dictionary that says A has the value 3, and then you link to a next or to an older one, right? That's, in this case, it would be nil, because that's, let's say, top level, right? Because it says, like our code actually says, like let A equals 3 in, and then this. Right? So this would be the top level one. But then when we update, we could say, okay, A now has value 4, and the older one is exactly this one. Right?
Yeah.
And then all we have to do is, when we go out of the let, we just restore, we're back to using this dictionary. Right?
That would be something that seems reasonable to implement in C, I think.
Yeah. So I'm actually going to use a form of this, except that my dictionary, each entry in the dictionary is only going to have one element. Right? So it's not really a dictionary. It just says, you know, A has the value 3, and B has, and then there's the rest. Right? So if you worked in dictionaries, you would have something like and B equals 2 in, right? You would also have B equals 2, right? And so on and so forth. But you could also just say whatever. I'm just going to have B is 2, and the rest is A is 3, and so on and so forth. Does that make sense?
So, well, if you get into like in the statement above, A equals 3 and B equals 2.
Mhm.
If you then change something to A, would you just recursively like call rest again until you reach?
Oh yes. You always have to traverse.
And then if you have okay.
So even here, if I kept B in the dictionary, right?
Mm-hmm.
It would also be in this dictionary here. And so even here, I would have to traverse to the older, unless I copy everything that's in the old dictionary into the new one, right? Then I could avoid traversing, but then I have to do the copying. Does that make sense?
Yeah, that makes sense.
Yeah.
So that way, if you renamed the value inside the let, so in the inner let, then we could access the outer variables A and B. For instance, if you have let A equals 3 and B equals 2, in that case C equals A plus B, that would be possible.
Well, in this case, so in this case here, right, my data structure would look like this. A would be 4, right? Rest is that. So if I look up A, I start here, I find it immediately. I know its value is 4 because I'm inside the let, right? If I look up B, I get 2. I can never get the old A because I always stop here. But if this were C, right, then this would be C. So if I look up C, I get 4. If I look up B, I get 2. And if I look up A, I get 3.
Okay, yeah.
Yeah. So all of these are possibilities. This is very simple. So we're going to do that.
To clarify, if you had like a function, well, I mean, just looking into the future, if you had a function and you called something that wasn't within the scope, but still existed in your data, cool, right?
I'm sorry, I'm not sure I understand your question.
So right now you're basically only adding to that data structure. You're not like removing anything from the scope of that, of the data structure. So let's say you had, you said let A equals 1 plus foo, and then foo, or we'll just say let A equals 1 and then B equals 1 plus foo, and then in foo you don't define A, you just call, you ask for the variable A in there.
Oh, wait, I'm calling foo?
Yeah, you're calling.
And foo is defined as just A?
Yeah, for example.
Oh, okay. So you're basically saying, I understand your question. So this is a separate function, right? We don't have functions yet, but we can think about it. If you enter a new function, the only things that are visible, the only names that are visible are the arguments to the function, right? So if you enter a function, you would do away with all your bindings, and you would make a new list of bindings that only contain the parameters and their values. You could, of course, say, okay, I'm too lazy. I wanna keep my thing, and I'm just gonna add X here, right? Because I'm lazy. In this case, this invalid program would work and give you the value for A, right? But this is an invalid program, so.
Okay.
Yeah. By the way, in some programming languages, so in Emacs Lisp, for example, that is actually valid. So in Emacs Lisp, you could write defun betay foo returns. Is that how you write it, or do you write it like that? I forgot how that works in Lisp. I think that is how you write it. And here I return betay A. Right now, if I execute betay foo, that's going to give me an error and say betay A is not bound, right? Void variable. But I could go let betay A be 1, 2, 3, and I call betay foo, and I get 1, 2, 3. It works in Emacs Lisp because in Emacs Lisp has so-called dynamic scoping, which allows this kind of stuff. In other Lisps, that is not allowed. So in Scheme or in Common Lisp or in Clojure, you couldn't do that because they have static scoping like Simplang.
Okay.
All right, so let's get to our code and figure out how to implement this data structure. So compiler.h. So let us actually call that our environment, because that is actually what it's usually called. So let's do type def struct environment t, and the environment has a name for the variable that is bound, and it has a value which I use in 64T4 value, and then it has a struct environment T next, test next, whatever. And now when I'm evaluating an expression, I'm evaluating an expression in the context of, I shouldn't say context. I'm evaluating an expression within an environment which contains the values that are bound, right? So I will change this here to have that env. So now we can already implement expr identifier, ident, I guess it is, which has this ident. So all I need to do is env lookup, and I'm looking up in this environment the identifier. Of course, I haven't implemented that function yet, but that function should be easy. A function that's more difficult is let. No, I shouldn't say function. An expression that's more difficult to implement is let. Namely, what do I have to do for let? For let, I have all of these bindings that I need to, for which I need to execute or interpret evaluate the expressions first, and then I have to bind their values to those names in my environment. So let's do that. We have one after the other for expr v dot let dot n. So the value is eval expr in my environment. Oh, also I need to change all the invocations of eval expr. And what am I evaluating? I'm evaluating expr v let bindings of I dot expr. And now what I can do is I can say env equals env, let's call it bind. So within the environment, I'm binding that expression's name to this value. And what it returns is a new environment that basically has this one struct prepended, right? Put in the front. And that's the environment in which I evaluate the next expression. So that stuff works, that stuff like this works, where you can do a equals a plus 1, right? So I'm evaluating this expression here first with the environment from outside. And then I get a new environment in which a is already bound to 3. And within that environment, I evaluate this expression, get 4 as a result. And that gives me a new environment in which a is bound to 4. And in that environment, I evaluate the body. Does that make sense? Yes, no?
Yeah, so far so good. Sorry.
So we've bound all the values to their names, and so all we need to do is we need to evaluate within the new environment, we let bindings, not bindings, body, I think is what I called it, right? The body. The nice thing is, I don't have to reset the environment to what it was before, because environment is just a local variable within this function. Right? So the caller's environment is still the same. Because what env-bind does is it doesn't actually change anything about the environment. It's an immutable data structure. None of it changes. I'm only prepending a thing that points to the old thing. I guess I should implement that so that it makes more sense. But first, I have to look at everywhere I do this and also pass the environment. And then, of course, we have one point where we call eval expr from the, did I call it driver main? Somewhere here, I call eval expr, and I can actually pass null as the environment. So let's now implement these two functions that we have, namely env-lookup, static int 64t, env-lookup, and what we get is an environment, and a name, and also env-bind returns an environment, a new environment. And it gets more complicated yet, but we'll get to that later. So we get a new environment, we get the old environment, and we get a name, and we get a value. Now, okay, let's implement lookup first, because that's easy. What we do is, we're running in an endless loop. We assert, because we're assuming that the name is bound, right? If the name is not bound, then we can die with an assertion. So what we can assert is that env is not null. Because we haven't yet found the name, so it must be somewhere. And now I can check if where we're currently looking for in the list, if that is our name, then I can just return the value. Call it value, right? Name value and next. Otherwise, env equals env next. So this is really just basic linked list search. Does that make sense?
Yeah.
Okay. Now env-bind is also very simple. It's just adding an element to the front of a linked list. Element new, and I'm going to call this env-alloc. And this is the complicated part that we'll get to in a minute. All I'm doing is I'm saying the name is the name, and the value is the value, and next is the old environment, and that's it, done. Right, so I never change anything about the old one. It really is an immutable data structure, at least for now, and I think we'll keep it that way. Now, the problem with the allocation is that we are allocating everything from our context, from the pool in the context. So the first problem is we don't have a context here. So we need to get the context into here, which might mean that we have to pass another thing, which I might not want to do. I'll think about that in a second. But then the second problem is that later on we will have loops in our programming language. And if you evaluate a loop, you also have to build environments. Even if the loop itself doesn't make new environments, there might be a let inside the loop, right? So each time you evaluate the body of the loop, you allocate a new environment. And we never free anything in the pool. So if we just allocate new data and we never free it, at some point we run out of memory and we don't have garbage collection. So that's bad. So what we're actually going to do is we're going to use a free list to wait. Can we actually do that? Yeah, well, not, yeah, okay. So we do actually have to free our environment, even if we use a free list, because how would the free list thing know what to put into the free list? So basically what we would have to do is we would have to say here int64t result equals, we're getting our result, and now we would have to say free the environment up to where it was previously, right? So free everything from env up to old being the old value of the environment. So basically we would free all the ones that we've allocated here, and then we could return the result. But what I'm actually going to do is I'm not going to allocate. So the reason why we used the pool in the context was that I didn't want to do memory management in the parser and in the scanner and in later on in the compiler, because they only run once, and their memory requirement is bounded, basically. But here our memory requirements are unbounded. And I could use the pool and then use a free list, but then I would have to pass in the context, and I don't want to do that. So I'm just going to use malloc and free for env free and for env bind. So env free, so here all I'm doing is malloc size of environment t. That's how we get a new environment, and env free static void old. So what this does is, while we are not at old, environment t next equals env next, free the environment and go to the next one. Does this make sense?
Yeah. That's just the normal linked list.
Yeah. So basically what we've done is there's some environment, right, that we have that comes from outside. And now we interpret a let. So we have a new binding that we put on here, and then we have another binding that we put on here. And then this is where old points to, right? This is old, and this is env. And all we're doing is we're traversing and we're freeing this one and we're freeing this one, and then we're back to here. Okay.
Mm-hmm.
Yeah, so I think that's it. Is there anything I forgot? Oh, wait,
I'm
no,
pretty
it's-
sure there's an argument missing somewhere, probably.
Well, we shall see. Yeah, of course. I need string.h. And in main, I need to now actually use eval. But other than that, I didn't forget anything. Now let's see what happens. Did I put the tests interpreter? Of course I did not. Ugh. Okay, what do we have in test parser? We let.sl and we have let many .sl. Let's just interpret these and see what happens. So what should we get if we run let sl? A is 1, B is a plus 1, which is 2, and then we add 1 plus 2, so we get 3, right? This should produce 3, correct?
Mm-hmm.
So simpling tests parser 1.6 let.sl 3. Then we have let many.sl, which should give us a1 plus a10, so 11. Or 11, hooray. And now let us actually, in the assignment, I have a few more difficult ones, or at least one difficult one. Oh, look at that. Let's go to tests. Interpreter 1.7. And put that into let.sl. And I think 3 is the answer, echo 3 to let.out. And we have this one, which should be minus 12. How do we call this? I don't know, let nest. Cat to let nest.sl. And what was it again? Minus 12. Echo minus 12. Let nest.out. And let's run it. Let's see what happens. Let nest.sl. Minus 12. So that works. I mean, this is the same, really. Well, whatever. Doesn't hurt. Let renamed.sl. Let nest renamed. Let nest renamed. And then also let's copy from parser 1.6 let many.sl and echo 12 at 11, right? Many.out. Then we can run our test thing. Test. Interpreter 1.7. Simpling. All right, there you go. It is done. Any questions? No. Okay. So next thing, loops. So in the next assignment, we're gonna parse loops and recur. The nice thing about loop is that its syntax is exactly the same as let, except that it says loop instead of let, so that's easy. Recur uses a syntax that is very similar to function calls, which we don't have yet either, but we're going to implement it here, so then later on it's not going to be a problem. And the way it looks is that each argument after recur is parenthesized. And the way the grammar works out is that if you get an open paren, then you know it's an argument to recur. right? So it's not like you don't have to think about, is it something from further up above? But the difficult part is that so far we haven't had to use a look ahead in parsing. Whereas here, if you are, let's say you are here at this point, right? You're here with your parser. So you have parsed recur, and you have parsed one argument for recur, which is mandatory. So there's at least one, you know that. And now you don't know, am I going to parse another recur argument? Or is it going to be something from above, which would be the end for this loop, right? So there could be an open paren here, or there might not be. So you need to look at the next token with a look ahead and potentially decide that you don't actually want to consume that token at this point because it's not the recur parser's responsibility to parse the end. Does that make sense?
Yeah, kind of.
So basically, you need to keep one token in advance that you can decide not to consume. Yeah, and that's that. And then after that, we will implement the loop. And at that point, finally, we can write some programs that actually compute non-trivial stuff. All right. Any more questions?
Nope.
Cool. Then thank you very much for dropping in, and I'll see you guys soon.
Thank you too.
Bye.
Okay, see ya.
Bye.